Okay, so we are actually going to do 11 and then 15 because I think 15 will be more useful before the two I have after it. All right, so 11 here though is yet another quadratic with another typo, but I don't think we're going to get 0 as an answer this time, so no worries there. All right, so 2 ugly squared minus 3 uglies plus 1 equals 0. And just our little reminder note at the top, we made a substitution. So that way we remember at the end, go back, because your answer should be theta equals, not u equals. All right. 2 times 1 is 2. And -2 plus -1 is -3. So -2u minus 1u is the same as -3u. Recopy the front, recopy the back, still equal to 0. Factor by grouping, 2u, u minus 1. We must factor in negative, and they don't have any numeric thing in common, so I'll just put a 1 as a placeholder. U minus 1, -1 times u, -1u, -1 times -1 plus 1. So this is equivalent. My u minus 1s are the same, so now I'm factoring them out. U minus 1 is up front, so I have 2u. U minus 1 is up front, minus 1. All right, so we have u minus 1 equals 0, so u equals 1. 2u minus 1 equals 0, so 2u is 1. U is 1/2. So sine theta equals 1, and sine theta equals 1/2. Now we have already done these a couple times, but sine is 1 at pi over 2. Plus 2 pi k. And the next problem, example 15, the 2 pi k is going to matter. And then here, where is sine 1/2? Short y is log x, that is pi over 6, and then 5 pi over 6. So we have pi over 6 plus 2 pi k, and we have 5 pi over 6 plus 2 pi k. Now they only said between 0 and 2 pi, so our actual final answer is just those ones we found on the unit circle. So we have pi over 6, pi over 2, and 5 pi over 6. I habitually write them in numeric order. I don't think WebWork cares. At least if it's programmed well, it won't care. Let's go with that. If somebody doesn't know how to program well, then, well, the problem ends up looking different. I know enough to know what it should look like, not saying I could actually make it do that thing, which would be sort the list before it checks it. All right. So a multiple angle trigonometric equation. So the ones after this now, which were before this, also do this. This one, like, it just focuses on the fact that it's a multiple angle thing. So I wanted to do it first, get this, like, out of the way as its own thing. So here we have the cosine of 2x equals 1/2. So, like, I could go to what is the cosine of 2x using an identity and solve that way, but I can also use my 2 pi k additions. So where's cosine 1/2? All right, so cosine 1/2 is short side with long side. So this is 60 degrees, so this is pi over 3. and 5 pi over 3. Because remember, all students take calculus, cosine's positive down there in quadrant 4. So I'm going to call that theta for a second here. So we've solved cosine of theta equals 1/2. We get pi over 3 plus 2 pi k. And we get 5 pi over 3 plus 2 pi k. But we don't really have theta here. We have 2x. So now I'm saying, well, okay, so 2x. Let me give myself a little more space. Y'all know how big I write. So now I'm saying 2x is pi over 3 plus 2 pi k. 2 times x. So if I want to get rid of the 2 with the x, it's being multiplied. So I would divide. And whatever I do on one side, I have to do to the entire other side. So not just the pi over 3 gets divided by 2, but the 2 pi k gets divided by 2 as well. Because that 2 inside the function makes it go twice as fast, which means we're going to get twice as many answers. All right, so we have divide by 2, divide by 2. So here, this divide by 2 is really the same as times 1/2. So we have x equals pi over 6 now, plus pi k. So if we're answering between 0 and 2 pi, my k value, when I put 1 in, pi plus pi over 6 is still within my unit circle. And then same thing over here. That 2x equals 5 pi over 3 plus 2 pi k. Divide by 2. And dividing by 2 is the same as 1/2 and over 2. So x is 5 pi over 6 plus pi k. Now there are some like weird observable patterns here, but you do it with the 2 pi k, just impact it as you do from whatever you're trying to get rid of next to the x. And then remember that you can plug in numbers for k. Sometimes you might even have to go back to like -1, -2, but usually you don't have to keep the k value, like it won't have to be super big. All right, so they did say 0 to 2 pi, and they put the parenthesis on the 2 pi. See, I told you those equals were typos. All right, so in my final answer, I have pi over 6. I have 5 pi over 6. I also have, so these are my k equals 0. Now I also have, if k equals 1, I get pi over 6 plus pi, and I get 5 pi over 6 plus pi. Now if I put k equals 2, then I'd be adding 2 pi, and then I'm out of the unit circle. Pi over 6, and I did -1, that's going to put me in the negatives. Same with 5 pi over 6. Pi is larger than it, so minus pi will pull it negative. So these 4 numbers are my list. Now I just need some common denominators. And so final list is also going to include 7 pi over 6 and 11 pi over 6. Pure fluke that it's like all these, not total pure fluke, but kind of pure fluke. Like, don't just assume if you got pi over 6, you're going to get all these others. It really does depend on what you had to divide everything by. So because we divided by 2, now these are angles that are only pi apart, which all of our straight lines across the unit circle, those are 180 degrees or pi radians apart. So that's why we're seeing angles that look very similar. It's only because it was 2 theta. And remember, when you're typing this list in, double check your commas, make sure they are next to the fraction, not underneath it. All right, so bad handwriting, but this is what happens whenever we have more than some number. When we have some number multiplied to x, we get that many number times as many answers. So if it was 5x, I would have divided by 5, and 2 pi over 5k is going to give me k equals 0, and then 1, 2, 3, and 4 will still be within the 0 to 2 pi range. So whatever number you divide by, that's how many k values you have to plug in to both answers. Because, there's usually 2 answers on the unit circle. All right, we're going to have one more after this.